because n is equal to 2, or n squared is equal to 4. It went from the second level to the first level. It went from 1/4 of this to this, and they're negative. So there is a loss of energy, and that energy has to go somewhere. And what happens to that energy?
It's offers light.
And would you say?
Same thing.
Okay. And so if we just dump energy into something like that, into some gas, and then see what light comes off of it, we can then start to actually see if Bohr's modeling is correct. So let's do that. Let's actually look into the light to see what comes off of it. All right, so what we're going to do is we're going to basically shine light. We're going to, try that one again. We're going to take a glass tube which has a particular type of gas in it, and we're going to run electricity through it. As electricity runs through it, it's going to excite the atoms in the gas, excite the electrons more specifically, which will go to a higher level orbit and then come collapsing back down, releasing light in specific wavelengths. Let's let it all the way, so don't stick your finger in it. How many have done this before? One. Don't want it too dark. All right, so what's going to happen here is light's going to come in through this, there's a slit over here. Light's going to come in and then get reflected onto this scale over here. These are in 10 to the negative 5th centimeters or 10 to the negative 7th meters. So where it says 5 right there, that's 10 times 10 to the negative 7th meters, or 500 nanometers. So we're in the visible light spectrum there. I think it's all there. It's just a matter of lighting. That's the part that I have to try to remember every time. So I need let's not touch that one. Oh. If you haven't seen it before, I do recommend come up and take a look. You're basically looking over here. If you block out the light, like as I did with my hand there, you should see a couple of bands of red, green, blue. See it?
It looks almost more like a yellow, orange, green, blue.
Okay.
Yeah.
I'm trusting that you're seeing it as opposed to pretending to. So we now have a way of, not only we can predict what colors will be coming out, but we have a way of being able to know what's in the sun. By seeing the light spectrum that's coming out of the sun, we can then start to piece together. And there's some woman, I'll say 100 years ago, Harvard professor, or she just working at Harvard, went through and categorized a whole bunch of suns based on this, went through the painstaking work without a computer trying to get all this matched up. I wish I could remember her name. All right, why don't we stretch our legs here, take a small little break, come back, and then start talking about why you're just a wave. All right. I didn't state this explicitly before, but when we talked about the photoelectric effect, talked about there was a threshold frequency for it being able to eject the electrons. Ultimately, it's because the energy of light is related to the frequency. And energy of light is h times the frequency. If we think about waves, there's the classic wave equation of the speed of a wave is the frequency times the wavelength. And so the frequency is just the speed divided by the wavelength. So if we're talking about light, that's the energy of it. And so, and frequency is this, so we get h v over the wavelength. And what's going to seem coming out of the blue, experimentally, they have found that the energy of light also is equal to the momentum times the speed of light. Oh, I guess I could make this a C here. So that the momentum of light is equal to Planck's constant divided by the wavelength. Or the wavelength of light is equal to Planck's constant divided by the momentum. It's just manipulation of letters at this point. And this is all concerning light. And then Louis Victor Prince de Broglie, and the last one, I'm attempting to say the French pronunciation of this. Anyone got a good French accent? Then we'll go with my bastardization, or later on I'll just say Broglie. Said all this is well and good for light, but we're talking about light acting like a particle and a wave. Well, if light can behave like a particle and a wave, why can't other things like electrons? Can electrons behave like a wave? Because we treat them as particles. What about us? Can we be waves? So he took it one step further and he said, well, the wavelength of things that aren't light, well, why don't we just adapt on that one and plug in our classical definition of momentum, the Broglie wavelength. So let's think about it from an electron's point of view. So the wavelength of an electron, come up with the speed here in just a moment. So it's 6.626 times 10 to the negative 34th joule seconds, divided by the mass of an electron, 9.11 times 10 to the negative 31st kilograms, times the speed of an electron, and I didn't actually write down the speed.
the same as its orbital velocity?
Yeah. We didn't do a speed at that point, did we?
I don't think so.
Well, I know that 1/2 mv squared is equal to, I'll go with the shorthand, k e squared over r 1/2 of that. Those go away. So the speed of an electron in some simple orbit, we'll just say the basic orbit, speed is k e squared over rm square root. So k, that's 9 times 10 to the 9th. Charge squared, 1.6 times 10 to the negative 19th squared, divided by the Bohr, assuming it's in the first orbit, the Bohr radius, which I had written over there. That was the 5.29 times 10 to the negative 11th. Times the mass, 9.11 times 10 to the negative 31st. Oh, and then square root all that. How fast is that electron going?
Uh, 2.19 times 10 to the 5th meters per second.
2.19 times 10 to the 5th.
Yeah.
Okay. Not relativistic. Still several orders of magnitude away from speed of light. And so what is the wavelength?
Uh, 3.3 times 10 to the negative 10 meters.
So recognize that the wavelength of light itself is on the order of 10 to the negative 7th, and so this is 1,000 times smaller than, very crudely, than light. It's not particularly big. But there should be some experiment that can be done to show that electrons, in fact, are behaving like waves. I mean, it's one thing just to play the math around with this, but let's take it one step further and see if there was an experiment. And of course, there was. The Davidson-Gerber experiment.
Actually got that to the negative 9.
Yeah, negative 9.
Yeah. Remember where I might have messed up. -34. -31.
The 2.19 is to the 6th, not the 5th. For the, on the bottom.
Oh, that's a 6 there?
Yeah, sorry about that.
Yeah.
Okay, fortunately, still not relativistic.
That's probably what.
Okay. So you were using the correct value here to get that?
Yeah, I just
Okay.
said the wrong exponent before.
Okay. And still below 10% the speed of light, actually, it's below 1% the speed of light. Davidson-Gerber. It turns out that Louis de Broglie was correct. Gets a Nobel Prize. He is the only person to get a PhD in physics for his doctoral dissertation. As his instructor, grad school said, it was 24 pages long. It probably didn't hurt that he was royalty. It's a royal connection. He was indeed a prince. And I think he lived off that figure for the rest of his life. So anyway, Davidson ends up getting a Nobel Prize for the work. Gerber does not. I wondered why Gerber felt like he got shafted there. Gerber just happened to be the grad student at the time. That before that, Davidson had done experiments with, the Davidson so-and-so experiments. But Davidson was the driving force there. And what he did was he shot electrons at the double slit experiment. Now, if electrons are a particle, what you would see is a whole bunch of electrons here and a whole bunch of electrons here. If it's a wave, we'd get a pattern very similar to what we did when light went through the double slit in I still want to say 1801, but somewhere early 1800s. And so, if it's a wave, then we get, the pattern here, where we get a whole bunch in the middle, and then not as many, then slowly, like that. And in fact, they got this pattern here. So then they took the experiment one step further. Instead of just shooting a bunch of electrons at the double slit, they decided to shoot one at a time. Now, as they shot one at a time, what would happen is that the electron would come through, and then when it hit the surface over here, it would scintillate. In other words, it would light up. And you send one through, and it hits here. You send the next one, it hits here. And then you keep doing it more and more. You do it a bunch of times, and you get a whole bunch in this region right here, and not many right there, and you get a whole bunch again in this area, and then a bunch in this area. Most of them in the middle. The next bit is in this next area right here, and then it sort of peters out as you go. But you definitely have these dark spots where electrons are not hitting. So this does give very tangible evidence for the idea that particles can act as waves. But of course, it's physics. There's got to be a way of describing this with math. How do you describe an object that is a particle and a wave at the same time?
When they first did the slit experiment, what kind of light are they using? Are they using like a lantern or something?
See, that's what I'm not sure of. It had to have been a really high-powered one by then. They had, well, within the early 1800s, Faraday was doing his experiments with batteries and watching current. So it's possible that they had, what Edison invented was a lasting light bulb. So it's possible that they had flashes of light, that they had the principle basically, we heat this up, it'll glow, it just won't last very long. So it's possible it was something like that, but I don't know. If it had just been lanterns, then the experiment could have been done, 100 years earlier.
Right.
It's probably somewhere out there on the internet, somebody's asked the question. You just have to wade through it all. All right. So enter a couple of huge names in quantum physics. Heisenberg. It's ERG. Yep. Schrodinger. That's that umlaut over the O. And Dirac. About to say Pauli, that would have just been ridiculous. Three major players, and there was about a 1 year period in the mid-20s, mid-1920s, where they came out with some seminal works in this, making them all future Nobel Prize winners.
How often did they give out those Nobel Prizes?
Once a year. And they can give it to several people. At this point,
I think just 3 people can get it.
only 3?
Yep.
Okay.
It's been an issue in the last couple of years, because nowadays most experiments are done by teams of hundreds.
Yeah.
Only the three leading people get that prize.
Which is why I was denied my Nobel Prize right there. That and missing out on the incredible breakthrough in physics, but besides that. All right, so Heisenberg. If we're talking about wave-particle duality, so suppose I gave you a wave that looked like this. Assume that it's drawn well. If I asked you what is the wavelength, would you be able to figure out what the wavelength is? With decent confidence?
Yeah.
All right. If I asked you, again, pretend this is going on for longer than I've drawn it. If I asked you where's the wave, where would you say?
Right there.
You sure it's not there?
Well, I mean, it's infinite.
Yeah, but it's hard to put down an exact location of it. So there seems to be this relationship here that, yeah, we can know one piece of information and not know another. If instead the wave looked like this, and I ask you to find the wavelength, do you have more confidence or less confidence or the same in being able to figure out the wavelength?
Probably the same. I mean, it's still just peak to peak. Or drop to drop.
Yeah, but peak to peak's a little less consistent now.
Yeah.
All right, how about the location? If you had to narrow down where this thing is,
Look, more confident.
yeah, at least it's not infinite. Because it does get to a certain point where, you know, it's small enough that we can pretty much say that it's somewhere around here. So knowing more of one thing tells us less of another. So let's think about it in terms of particles. Do a pseudo derivation. So if I had to identify the position, and I cannot seem to find the marker, which actually is dark.
This one.
That probably is it. Thank you. So assuming it's sort of one-dimensional here, this is going to be equal to, oh, much better, bx times t. In other words, there's a range here where we can find this particle. And I know speed is just momentum over the mass. And so I can find out this time interval. So if I have an object that's moving